So let's just revisit this profile business and show how dry convection is actually a stable process. Okay, where does it happen? Essentially in deserts where the air is very dry and daytime heating can create warm air at the surface, and the air rises. Because the moisture is basically zero, it's going to be dry convection, right? Convection is any partial movement in the vertical, and if it is dry air, it's going to be dry convection. If it has moisture, it's going to be moist convection. So we have seen this profile before, even though we kept showing it as mostly linear. If you paid careful attention, you would have probably noticed that it's not so linear. But nonetheless, here it is just the climatological atmospheric temperature. What is a climatological atmospheric temperature? So if you measure a bunch of temperature profiles on many places around the Earth for many years, and you just average it over all the years and all the seasons, this is how it would look on average up to the tropopause, and then stratosphere is up there, which we haven't shown completely. And as I said before in the previous podcast, it is very common to show the height in the atmosphere in terms of a pressure coordinate. Pressure decreases with height as well, as we can see here. 1000 millibar is close to the surface, 200 millibar is basically the top of the atmosphere. And this is a nonlinear profile, and we want to see if you just heated the surface in the desert and the air moved up, will it be stable or will it be unstable, right? So that's dry convection. The other things here we will look again when after we define dry potential temperature and moist potential temperature. And you can see that dry potential temperature is basically the opposite almost of just the plain temperature, which we said is not conservative. We'll see that this is conservative except when you have moist processes, and this is much more vertical than either of these. This is the moist potential temperature, and we'll see that this is conserved under moist processes as well. This is conserved under dry processes, and this is conserved under moist processes. So we need conserved quantities for making life simple and trying to track things. If things are not conserved, then obviously it's not easy to understand the processes, solve the processes, predict the processes, and so on and so forth. It turns out to be very simple. If you take an air parcel at any pressure and bring it down to a reference pressure, let's say pressure at the surface, then what would be its temperature? Okay, so you always reference the parcel of air to a particular pressure so that all the parcels you're measuring are referenced to the same pressure. That's the dry potential temperature, and you add complications of moisture and you get moist potential temperature. We'll formally define them soon. Okay. So looking, again, sorry about that. I hope this will work when I go back to the display mode. Otherwise we're going to have a problem. So looking at the environmental profile of temperature again, see that we have shown it as a straight line for simple purpose, for idealized depiction, but nonetheless we have just think of it as taking the linear part of the lower atmosphere here. Okay, so what is a dry convection? Basically you have a dry adiabat. We defined that as gamma d. If you move a parcel of air, so this is where you have to get used to this. There's an environmental temperature profile, and then we have dry adiabat and moist adiabat, which means if we move a parcel of air that is dry and we move it adiabatically fast enough not to mix heat with the environment, then how does it behave? So we have to always carry the environmental profile and the path of the parcel. That's the main complicating factor. So if you move a dry parcel here beyond the environmental temperature and it's colder, then it's going to get heavier, so it's going to want to come back. There are no complications involved like condensation, heating, and so on. And if you move the parcel away from the environment towards a warmer temperature along the dry adiabat, because it's a dry air parcel and will move along the dry adiabat, it'll get warmer and lighter, so it'll move back towards the environmental profile. That's all. Okay, move here, you get heavier, you want to come back to the environmental profile. Move this way, you get warmer and lighter, and you want to come back to the environmental profile to the appropriate buoyancy level. So atmosphere mostly remains stable to dry processes like dry convection, which does happen in deserts. Okay, that's the main message of dry adiabat and dry convection.